Started. Go.
Hello, good afternoon. Thanks for inviting me.
Wait.
Sorry.
Uh, so we just so just because there could be 1 or 2 seconds of delay, so just wait a bit and then I introduce you so that if I'm cut, it doesn't matter, and then you can
Okay,
start.
cool. Sorry.
So welcome everyone. Hopefully the stream started. So we have the pleasure to have Shiv Yadavalli, who will talk to us about contextuality in entanglement-assisted one-shot classical computation. Okay, you can go, and I mute.
Thank you. Good afternoon. Thanks for inviting me to QPL. So today we'll look at the role of contextuality in entanglement-assisted one-shot classical communication. So this was joint work that was done with Ravi Kunjwal, and it started when I was a summer undergrad at Perimeter Institute in 2018. So actually, our work has just been uploaded to archive as a preprint like last night, so you guys can see it. We've pinned it on the channel also, so you guys can look at it. So let's start. So we'll be looking at connections between three distinct areas of quantum foundations and quantum information. One is contextuality, specifically Speckens formalism of contextuality, then entanglement-assisted one-shot classical communication, and then briefly about non-local games. So first we'll explain these three individually. First, let's talk about contextuality. To consider contextuality, we first talk about operational theories, specifically prepare measure experiments. So in prepare measure experiments, we first have a preparation procedure that produces a preparation outcome that is labeled classically by some symbol X. And then we have a measurement outcome for this that we apply on this preparation, and we get a measurement outcome given by X prime. Just to be clear, X and X prime are just distinct variables. There is no relationship between the two. They can have different cardinalities. In our operational theory, the quantity that we care about is the joint probability distribution, X and X, preparation and measurement outcomes X and X prime, given preparation measurement procedures P and M, as shown here. Now, our operational theory is just a catalog of data. If we want some explanatory power, we posit that there exists a causal intermediary or an ontic state, and thus posit an ontological model. An ontological model is a causal intermediary that propagates the effects from our preparations to our measurement. And thus we see that this joint distribution that we considered earlier breaks up into a preparation distribution and a measurement distribution, where this ontic state lambda is produced by the preparation, and it conditions the effects of our response functions. Now we want to make some kind of reasonable restriction to our ontological model that in some sense recovers a notion of classicality. And for this, we define non-contextuality for both our preparation and measurements. Non-contextuality is motivated by Leibniz's rule, which is essentially an equivalence between operational equivalence and ontological equivalence. Thus, things that are operationally equivalent should also be equivalent in our ontological description. So first, if we consider that for preparations, if two preparations are operationally equivalent, that is, there exists no measurement that can distinguish between these two measurements, as you can see here, then in our ontological theory, they should be described by the same distributions. Similarly, two measurements, if they're ontologically equivalent, if two measurements are operationally equivalent, that is, there is no preparation for which they produce different statistics, then again, in our ontological theory, they should have the same distributions, as we can see here. The response functions should be the same in our ontological theory. Okay. Now we look at two examples, one for preparation non-contextuality and one for measurement non-contextuality, just to bring us in context. One is bipartite entanglement. Now, if we consider the case where Alice and Bob share an entangled state, and Alice steers states on Bob's side, different measurements that Alice does on her side of the state would be counted as different preparation procedures that Bob experiences, because different states are steered onto Bob's side. But we see that the reduced state on Bob's side is independent of the measurement choice that Alice does. That is to say that the different preparation procedures that Bob experiences are all operationally equivalent. Thus, we would say that up up to coarse graining of measurement outcomes of Alice that Bob obviously does not have access to due to no signaling, both these ensembles are operationally equivalent. Thus, we can say that due to this operational equivalence between ensembles on Bob's side, the ontic state does not the ontic state should not be conditioned by preparation procedures, because we saw that operationally it was not conditioned. Thus, we in this expression of our ontological model, we remove the conditioning of our ontic state we remove the conditioning of preparation procedures on our ontic state, as we can see here, and thus replace it just by nu lambda instead of p lambda given p sub I. So we don't have any conditioning with respect to preparation procedures that Bob experiences. So that's preparation non-contextuality as an example. Another example is measurement non-contextuality, where we consider a hypergraph theoretic representation. So this is actually much more simpler to understand. If we consider two different measurement POVMs, M1 and M2, and both of them are four outcome POVMs in our case. If the second outcome of the first POVM and the third outcome of the second PM, just as an example, have the same statistics up to post-processing for every single preparation possible, then we would say that these two measurement events are operationally equivalent. And thus, when we consider an ontological model where we give probability assignments, we have to assign both these measurement events the same probability, and thus we represent this visually as two hyperedges in a hypergraph that share that specific vertex. So this guy and this guy is this guy that is shared by these two measurements. Okay, so that's contextuality. So we're done with contextuality. Now let's come to a quick introduction of entanglement-assisted one-shot communication. So first, let's talk about one-shot classical communication, which is just the fact that I have Alice and Bob, and they share a classical channel between them. A classical channel is characterized by a bunch of symbols with Alice, a bunch of labeled X, a bunch of symbols with Bob labeled Y, and a classical channel that is characterized by conditional probabilities for Y given X. And the important point here is that because you obviously are communicating, there is signaling, and these two parties, Alice and Bob, are time-like separated. We are considering the one-shot regime where we use this classical channel only once. There was a lot of work done in this in the 1950s by Shannon, who essentially saw that capacities of classical channels can be thought of as the independence number of the hypergraphs and the graphs associated with this classical channel. So let's just understand this hypergraph representation of this classical channel. So all the vertices represent input symbols, and all the hyperedges represent output symbols. And an output symbol encompasses all the input symbols that could have output that specific output symbol. So 2 here encompasses B and C. That means that you could have gotten the output 2 whether you pressed input B or input C probabilistically, right? This is an example. Now, next we can talk about message encodings, which is disjoint partitions of our input symbols, which are vertices of our hypergraph. And this is a noiseless encoding. That is to say that by getting a specific Y symbol, Bob can know exactly what input was sent. As you can see, both these inputs are disjoint in the hypergraph. But here you see these are no more disjoint because you have some output symbols that can confuse you. If you get one of these output symbols, you're not sure whether you got an A or a B, and thus you don't know whether start was sent or stop was sent. So these are noisy classical channels, and these would be the ones of interest for us. So this is just the general. So one way of encoding, one figure of merit for classical channels is capacity. Another figure of merit that we specifically look at is success probability. That is, we fix a specific message encoding and then ask the question, what is the success probability on average? So Alice will choose some message with some probability, then choose some vertex inside that partition with some probability and input that into the channel, get some output with Y, and then Bob will, with some strategy, infers what message Alice wanted to send with some probability, and thus you can just compute, sum over everything. You can compute the success probability, which is the case when M is equal to M prime, thus this delta function. So you have some encoding by Alice and some decoding by Bob, and you have this classical channel in between. So until now, everything was classical. Now we can add some quantum infrastructure to a problem where we have entanglement assistance between Alice and Bob. So Alice and Bob don't just share a classical channel, they also share an entangled state. And they can perform local measurements on each side, as you can see here. The measurements obviously output some classical output, as you can see here, X and M prime. So this is the protocol. I'll just describe the protocol. And this is the protocol that we mean every time we say entanglement-assisted one-shot classical communication. From now on, I will not say one-shot classical communication and all that. I'll just say entanglement-assisted communication. Just a second, sorry. Right. So the protocol that we're talking about is, so Alice thinks of some M, and then Alice performs a measurement on her side of the state row AB and gets some classical output. Based on that classical output, she inputs a symbol in the classical channel, and Bob receives an output. Based on the knowledge of that output symbol that Bob saw, Bob will perform a measurement on his side of the entangled state, and then infer from the result of that measurement, he will infer some M prime. And the question is, how often is M prime equal to M? So this is just a general expression. Now, how this expression looks exactly like what we saw earlier. So what's the difference? The difference essentially comes from the information that Bob has access to. Bob has access, in the classical case, has access only to the symbol Y that comes out of the classical channel. But in the quantum regime, he has access also to a state that Alice has steered by her measurement on her side that she did before she entered a symbol into the classical channel. So Bob is not just conditioned by Y, but is also conditioned by M and X through this steered state on his side of the entangled state. So Bob can perform a measurement based on the knowledge of Y, that is the output symbol that he got from the classical channel, and perform a measurement on the state that he has access to on his side of the entangled state, and then based on that distribution, decide what has to be the M prime. Based on that output, has to decide what has to be the M prime on that he should. That would be the best guess for what Alice intended to send. So that is entanglement-assisted communication. Now we can talk about the third thing in our triangle, which was non-local games. Now, non-local games, Alice and Bob don't talk to each other. They're space-like separated parties that don't talk to each other, but they share an entangled state and can perform local measurements on either side. What happens on the so the way that this game is played is that there is a referee that sends questions here labeled M and Y to Alice and Bob. Alice and Bob have to coordinate their answers in some manner, and to aid that coordination, they can use this classical channel. I'm sorry. They can use this entangled state. There is no classical channel here. My bad. So there is no classical channel. They don't communicate with each other. They're space-like separated. They have an entangled state that they can use. And the question is, can they do better than just? Can they do better using entanglement correlations than if they just had classical correlations? And there's a lot of work that says that yes, that is true. You can do that. For example, the thing that started all this off, the Bell experiment, is an instance of a non-local game. Okay, so now we have looked at three different things. So let's just recall, we spoke about contextuality, we spoke about entanglement-assisted communication, and we spoke about non-local games. Now we look at the interplay between these three ideas. So first, let's start with entanglement-assisted communication. We can show that entanglement-assisted communication is driven by preparation contextuality. Right? So to prove this, we actually consider the contrapositive, which is the case where we show that preparation non-contextuality is actually a signature of classicality. So if you write out the expression in the preparation non-contextual regime, it is rather obvious that what you see, the result that the expression that you see is the same expression that you would get in the classical case. Thus, it is very easy to notice that the maximum success probability in the preparation non-contextual case is the same as the maximum success probability in the classical case. Thus, any notion of quantum advantage is because of preparation contextuality. So that's the first result that we have. Then we just have a small mathematical aside where this was something that was noticed in a paper by Cubitt et al. In 2010. We'll talk more about this paper later also. But in the 2010 paper, Cubitt et al. Show a construction between that is that is motivated by entanglement-assisted communication, specifically the hypergraph structure of the classical channel that is being used in this entanglement-assisted communication protocol. As you can notice here I show the exact rules that are used for this non-local game, and these rules use the hypergraph structure. So here you can see the 0 cases where there is no support, and the greater than 0 cases where there is support. So what they're using is the hypergraph structure of our non-local of the entanglement assisted communication channel. So yeah, that, and using that they define the non-local game. So given this mathematical correspondence, we can prove that for a certain class of classical channels, here we call them output uniform k-regular classical channels. Output uniform just means that all the outputs for a specific input are equally likely, and k-regular just means that there are equal number of outputs for any given input. So that's very nice symmetric case. In this symmetric case, and if you consider their corresponding non-local game as was prescribed in the Qubit et al. Protocol, we showed that if there is a quantum advantage in this time-like separated entanglement-assisted communication protocol, there is also an advantage in the space-like separated non-local game, right? And in our results, you can very clearly see that it is you can also reproduce the specific case that Qubit et al. Were considering, which is the zero error case. So we'll talk more about the zero error case in a bit, right? This framework also applies specifically, this framework also applies, for example, to the communication task that was studied in an experimental paper by Prevedel et al., where they demonstrate experimentally this quantum advantage due to entanglement assistance, and the specific classical channel that they consider is based on the CHSH non-local game. So we can see this interplay of these ideas again. And our framework encompasses both of these. Now we consider the generalized Qubit et al. Protocol. So in Qubit et al., their paper essentially shows, their paper is essentially about the improvement that you can see in the zero error capacity. So what they notice is that classically, so if you first, they are motivated by the Cochin-Specker hypergraphs and the Cochin-Specker sets. So that's where the link to contextuality more or less comes. So first you consider, they saw that classically, if you consider this hypergraph, which is the Peres-Mermin 24-ray construction, this is uncolorable. Thus, you can send at most five error-free messages. So you can send 5 zero-error messages. But if you assess this quantumly and use the fact that you have KS projective measurements, you can suddenly send 6. Right? You have orthogonal bases associated with each of these, and each of these hypergraphs. Hyperedges are also orthogonal bases. So thus you can do these. You can have the schema of measurements where you can get where you can figure out outcomes with 100% probability. But clearly, this is experimentally untenable because we don't have noiseless measurements of states. So we generalize this protocol to noisy measurements in states. And instead of looking at the zero error capacity, we rather look at, if we fix a specific encoding, what is the success probability? That's what we considered earlier. And yeah, so that's what we consider. And we still use the same entanglement assisted communication protocol that we mentioned earlier. So just a reminder, vertices are inputs, hyperedges are outputs, and the purple dotted hyperedges are the messages that I'm wanting to send, and these hyperedges are just measurements. So just sorry, let me just get back to this. So messages. Just give me a second. Sorry. So messages that are performed, messages that want to be sent correspond to Alice's measurements, and outputs that are received would correspond to Bob's measurements, which would be these purple dotted hyperedges for M and just the normal hyperedges for Y. Cool. So that's that. So now, until now, we've only spoken about preparation non-contextuality. We want to bring measurement non-contextuality into this picture. So just to remind ourselves, preparation non-contextuality, the maximal success that you can get in the preparation non-contextual regime is the maximal success that you can get in the classical regime. But if we introduce measurement non-contextuality, we further restrict our response functions. So clearly, we do not have an equality, we only have an upper bound. Now we can ask the question, when is this upper bound saturated? Now, sorry, this upper bound is saturated when Bob when we actually restrict the information that Bob has. If Bob knows only about the classical channel hypergraph and does not know anything about the exact channel probabilities of the classical resource that these two guys, that Alice and Bob share, then can recover we can recover this equality. What we see is, so this motivates the assumption that we call context independent guessing, where Bob's guess of, or Bob's inference for what x prime is, or for what input symbol Alice sent, is independent of which specific output symbol he got. He only cares about the support. So overall the different output symbols, the probabilities are equal. That's this delta function. So there is no weighting. So different y's have the same weighting. In this, so this we call CIG. So if we make this assumption of CIG to our classical inferences that Bob can make, then we restrict the kind of inference strategies Bob can use, and then we recover an equality that says that the success probability for general non-contextuality, that is both and non-contextuality, is equal to the maximal success probability in the classical regime, assuming that Bob's inferences are restricted by CIG. Okay. Now that we have this graph theoretic framework that we've spoken about, we invoke ideas that were brought up in Ravi's earlier papers in 2019 and 2020, where he talks about certain correlation functions that witness non-contextuality. So these correlation functions consider the correlation between preparations and measurements on Bob's side. So this is on only one wing of the bipartite experiment. And these depend only on the quantum infrastructure. They only care about the preparations that are induced on Bob's side and the measurements that Bob can perform, right? So if you just consider that setup on Bob's side, we see that if we assume non-contextuality, both preparation and measurement non-contextuality, this core quantity is upper bounded by a non-trivial number beta that depends essentially on the hypergraph structure. It's called the weighted max probability. It depends only on the hypergraph structure. Now, if we have, but what we see is that in quantum mechanics, this core can go up till can violate this inequality, and thus it becomes a witness. This inequality is a witness of non-contextuality, and a violation of that is a proof of contextuality in quantum theory. We use this quantity because it sort of naturally comes up when we are trying to bound our success probability of our entanglement-assisted communication protocol. So if we consider our entanglement-assisted communication protocol, assuming that Bob's classical inferences are restricted by CIG, then we see Bob's classical inferences are restricted by CIG, then we see that the success probability is upper and lower bounded by this term that includes this correlation function, and it also includes this eta. Eta is the confusability probability of input symbols. It's the probability of Bob inferring, x prime instead of x when Alice actually sent x. So it's the minimum confusability and the maximum confusability that is there. So the important part about this inequality is this inequality, both the upper bound and the lower bound, separate the quantum infrastructure, the properties of the quantum infrastructure, which is core, from the properties of your classical resource, which is the classical channel, which is eta. So these two things are separated, and it's actually symmetric in both these terms, as you can observe. A notable special case of this is the case when all symbols are equally confusable, which is the case when eta max is equal to eta min, which is equal to eta, which happens when you have uniform channels, as for example, the case that is considered in Cubitt et al. So in that case, you can show that if you're in the contextual regime, that is, core violates this beta upper bound, then this is equivalent to saying that you will have a quantum advantage. So your success probability will exceed the non-contextual regime, a maximum success in the non-contextual regime, which is equal to the success probability in the classical regime. We are anyway assuming that Bob is making, we have the assumption of context independent guessing on Bob's side. So this clearly provides an application for the non-contextual inequalities, the graph theoretic inequalities that we had already considered, that Ravi considered in his 2020 paper. Yeah, so I think with this we are done. So I'll just summarize. So we have, so we've shown three things, three main things, other than a bunch of side stuff. That is, first, that preparation contextuality is what drives quantum advantage and entanglement-assisted one-shot communication. Second, quantum advantage in a class of entanglement-assisted one-shot communication protocols is equivalent, happens if and only if quantum advantage in the corresponding non-local game occurs. It's important to realize that both of these are two different physical scenarios. So this is only an if and only if. This is only a mathematical correspondence. And then we use these graphs. Then we go further, introduce measurement non-contextuality, and we have an application of non-contextuality inequalities to bound our success probabilities of entanglement-assisted communication success probabilities using these graph theoretic invariants that we saw earlier. So this is an application for those inequalities, in some sense operationalizes them. As you can see, a lot of this work has natural directions of future work. An example of this is, so one case that we can consider is there a possibility for constructing non-local games for any classical channel that also satisfy the properties that we saw earlier, sort of this correspondence that we saw? Is this possible? Is this true for all classical channels in some sense? Another is, can we talk about quantum advantage for general classical channels for entanglement assisted protocols, and what is the role that Coach and Specker sets and hypergraph frameworks play in that scenario? And another is the question of channel simulation. That is, can we say anything about what are the resources required to simulate a less noisy channel from a more noisy channel, using quantum resources like entanglement and quantum measurements, or contextuality for that matter. So that's my talk. I think I'm here for questions. Just as a quick summary, what we've looked at is we've looked at connections between Coach and Specker hypergraphs and entanglement-assisted protocols and non and Speckens contextuality and non-local games. We've looked at how there are lots of connections and there's a lot to be studied between as interplay between these four areas. Yeah, thank you. And I should thank Ravi for all the help and guidance that he did through the last 2 years when we were doing this work. Yeah, so thanks, Ravi. I think he should be available in the Slack channel post this. So if there are any questions, please, you guys can go ahead.
All right, thank you very much. So there are already questions in the Slack. In the Slack channel. So one question is, what constraints are on the hypergraph to get the equivalence on the slide just before the summary and the conclusion?
Let me just,
I guess.
this one?
The equivalence, the slide just before the summary and conclusion. So I guess the one just after.
Right here?
Yeah.
Right. Yeah. So here we are considering Cauchy-Specker hypergraphs. So we are considering Cauchy-Specker hypergraphs. So so all this definitely works for Cauchy-Specker hypergraphs. But other than that, yeah, there isn't any other constraint on the hypergraph per se. Yeah, there isn't anything on the hypergraph per se other than yeah.
Okay, and maybe one last small question before closing this stream. Does the result translate to advantage in channel capacity in the asymptotic setting?
I'm sorry, can you repeat the question? I couldn't hear it.
Sorry. Does the result translate to advantage in channel capacity in the asymptotic setting?
Yeah, so we have not studied the asymptotic regime, so I can't specifically tell an answer. But one thing that I know is that entanglement assistance has been studied in the asymptotic regime, and I believe that I think it's been done by the same Cubitt et al. There is some subset of those authors who've also worked in on the asymptotic case, where I think they do prove that even in the asymptotic case, there is a quantum advantage. Now, whether there is a link to contextuality is something that we still have to probe. But yes, I believe quantum advantage occurs even in the asymptotic limit.
All right, thank you. So it's now 4 p.m. in France. This closes the session. So I invite you to thank the speaker in the Slack channel. And if you have more questions, do not hesitate to ask them there. Thank you.
Thank you. Bye.